Hello everyone. So today's video is related about Poisson's and Laplace equation. So these two equations are very important in solving the problems in electrostatics. So we know some methods of solving the electric field intensity or electric flux density using Gauss law or Coulomb's law. But in practical situations, the charge distributions over the complete surface is not known. Instead, we know only about the surface charge distribution. Suppose if you take a parallel plate capacitor, the charge distribution in the boundary only we know, and we have to find the electric field intensity by knowing only the charge distribution in the boundary. So in that situation, we can't apply directly Gauss law or Coulomb's law. We have to solve the problem using Poisson's or Laplace equation. So that is the purpose why we are going for Laplace equation. Now we will see, we will derive the Poisson's and Laplace equation from Gauss law. So we know that del dot D equal to rho V, D is equal to epsilon into E. So this is E is equal to minus del V. So if we are substituting E here, so del dot of minus epsilon into del V equal to rho V. So del square V is equal to rho V by epsilon. That is the Poisson's equation. So you, what is rho V? Rho V is volume charge distribution. Epsilon E, epsilon is the permittivity in the medium. Suppose the charge distribution is 0, then del square V equal to 0. That is the charge density. If it is a charge-free region, free space. For that case, del square V equal to 0, which is called as Laplace equation. So if you apply the Laplacian parameter, that is del square V, in terms of this differential form, we can write it as dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square equal to 0. This is in Cartesian coordinate system. The corresponding Laplace equation in cylindrical coordinate system and spherical coordinate systems are given in these equations. So now we are going to see three types of capacitances. How to find the capacitance using the normal method and how it differs from the Laplace equation method. So we can solve the capacitance using normal method. Normal method is by definition of capacitance, capacitance equal to Q by V. Capacitance equal to Q by V. We have to find Q and V. Okay, V is equal to E dot dl, integral E dot dl. And if you know the value of E, then you can find V. Then you have to substitute Q and V in order to find C. That is a normal method. By using Laplace equation, we can solve the problem. So how simple it is? That is how we, that is what we are going to see. So we are taking a case of parallel plate capacitor first. So capacitor is defined as the ratio of Q and the potential difference between the two plates V. So here we are taking two plates which are separated by a distance of D, and the charges are distributed in the plate with a charge density rho s. So in one of the plate the charge is negative and another plate is distributed by positive charges. So here you have positive charges, here you have negative charges, and the electric field is normally oriented from positive charge to negative charge. So rho s coulombs per meter square, this is rho s coulombs per meter square. So the electric field intensity in the first plate is given by rho s by 2 epsilon. Similarly, rho s by 2 epsilon into an, here you have minus the second plate. So this is the given electric field intensity in the corresponding plates. So what is the total electric field intensity? We have to add both E1 plus E2. So rho s by 2 epsilon into Az plus rho s by 2 epsilon into, we are taking the magnitude only. So rho s by epsilon into Az, that is the total electric field in both plates. The electric field is oriented perpendicular to the plate actually. So here you have, this is the plate. So perpendicular to this plate, the electric field is oriented. So from electric field intensity, we can find V. So V is equal to minus E into dl. So minus of rho s by epsilon into Az into dl. What is dl? In Cartesian coordinate, we can write it as dx ax plus dy ay plus dz az. So rho s by epsilon into Az dot is dl. So rho s by epsilon into dz, okay, 0 to d, that is the length between, that is the distance between the two plates. Here you have dz. So minus rho s by epsilon into d. Okay, that is V. So what is the capacitance? Capacitance is Q by V. So rho s into A, that is Q is what? Q is equal to rho integral rho s into ds. So ds is, when you integrate, it is total area of the plate. So rho s into A. So this is V, we have already derived. So rho s into d divided by epsilon. So there is rho s gets cancelled. So the capacitance is epsilon A by d. So this is the normal method of solving the capacitance. That is by finding the voltage difference between the potential difference between the two plates, and we have to substitute Q and V. So Q by V will give the capacitance value, where epsilon is the permittivity of the medium, A is the area of the surface, area of the plate, and D is the separation between the two plates. So this is epsilon naught, epsilon r A by D. So because epsilon is equal to epsilon naught into epsilon r, where epsilon r is the relative permittivity of the medium. The same problem can be solved by using Laplace equation. So this is Laplace equation, del square V equal to 0, dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square equal to 0. So it is a one-dimensional problem because we are considering the separation between the two plates along the x-axis. Okay, so the plates are placed in YZ plane. Okay, so the variation is along only in the x-axis. So this problem we can apply Laplace equation to solve the capacitance. So this equation becomes, this Laplace equation become one-dimensional for this problem. So dou square V by dou x square equal to 0. So when you integrate on both sides twice, then V equal to Ax plus B, where A and B are constants and they can be obtained by putting the boundary conditions. So at x equal to 0, that is the lower plate, the potential difference is, because this is the ground and this is the maximum voltage it's applied, V naught. So when you substitute x equal to 0, V equal to 0, then V is equal to 0. And when you substitute at x equal to D, V equal to V naught, okay, V naught equal to A into D, because x, so this B is 0, so x becomes now D, V is equal to V naught. So V naught equal to A into D. So A is equal to V naught by D. So this equation becomes V naught equal to, okay, that is V is equal to V naught by D into X. So that is the equation we have solved. That is the potential difference. Now what is E? E is equal to minus del V. So when you substitute this one here, instead of V naught by D into X, with respect to X, we have to differentiate. So V naught by D, dou by dou X of X is 1. So V naught by D into X. So D is equal to epsilon into E, epsilon V naught by T. That is the electric flux density is equal to epsilon into E. Now what is Q? Q is equal to, this is Gauss law, Q is equal to D dot ds. So D is equal to epsilon into V naught by D dot ds. ds is dy dz into Ax, okay, because the plate is in the YZ plane. So the area is dy dz into Ax. Why Ax? Because this area, the normal vector is perpendicular to this surface. Okay. So when you solve this equation, epsilon V naught by D into A, where A is the area of the parallel plate. So Q by V naught, epsilon V naught A by D divided by V naught. So V naught gets cancelled, epsilon A by D. So this is by Laplace equation method for getting the capacitance of parallel plate capacitor. So which is simpler than the normal method of solving capacitance. Okay. So this is the advantage of Laplace equation for solving the capacitance. So same method we can apply for spherical capacitor as well as coaxial capacitor, because the coaxial capacitor is very important in the case of coaxial cables, coaxial transmission lines, which are practically available in transmitting the signals from one end to another end. So I hope this video will be useful to you. So if you like this video, you can subscribe our channel, you can like this video, and you can put the comments in the comment box. Okay. Thank you, Nanda.